So we've made this definition of the dimension of a vector space. If we have a vector a subspace in Rn, a subspace V, then the number of vectors in a basis for V is called the dimension of V, and it's written dim V like this. And this makes sense because no matter which basis for V you choose, the number of vectors in it is always the same. The vectors themselves might be different depending on the basis you choose, but the number of vectors is always the same, and that's what we call the dimension. So let's actually calculate the dimension of a couple of vector spaces. Here's one example. Find the dimension of this. Well, one nice way to find the dimension of a vector space is just find a basis for the vector space and then just count up the number of vectors in that basis. And of course, to find a basis for the vector space, we need to find a collection of vectors that spans the vector space, and then hope that it's linearly independent. So for this particular vector space, we can write V in the form x times 4, 0, 1 plus y times minus 2, 3, 1. And this is where x and y are in R. And that means that this is the span of these two vectors, 4, 0, 1 and minus 2, 3, 1. So if these are linearly independent, then we must have a basis. But when you have only two vectors, they're linearly independent as long as one isn't a multiple of the other. But that's clearly the case for these two vectors. Neither is a scalar multiple of the other. So these two vectors are linearly independent, and they span V. And that means that this collection of vectors, 4, 0, 1, and negative 2, 3, 1, is a basis for V. And that means that the dimension of V is just the number of vectors in this basis, and that's 2. So this subspace has dimension 2. All right, let's look at another example. How about the dimension of this vector space? Well, we already have a spanning vector for this a spanning set for this vector space W. Just these three vectors span the vector space because that's the definition of W. W is the subspace spanned by these three vectors. We just need to check if these are linearly independent. So to check that, remember what we usually do is we put these all into a matrix, and then row reduce the matrix to check if it corresponds to a system that a homogeneous system that only has trivial solutions. And this will have only trivial solutions if this matrix row reduces to the identity. In this case, to the identity. In general, you have only trivial solutions if this matrix row reduces so that there's a pivot in every column. In other words, no free variables. So let's just do a quick row reducing. We're going to have to subtract row 1 from row 3. So let's see, that's going to make this 0, and that's going to make this 4, and that's going to make this also, I'm sorry, it's going to make this 3, and this one 4. I'm sorry, no, this one is also 3. All right. And then we can subtract 3 times row 2 from row 3, and that gives us 1, 1, 2, 0, 1, 1, and then 0, 0, 0. So this is telling us, first of all, that these vectors, because this row echelon form has a column with no pivot, that means that these 3 vectors are linearly dependent. But that doesn't really tell us, well, how many of these vectors do we need to keep to still have the same span? Well, if we write down the actual solutions to this homogeneous system, what we get is, I guess we can do one more step in our row reduction just to eliminate this 1 here. We get 1, 0, 1, 0, 1, 1, 0, 0, 0. Okay, so because there's a free variable in this third column, so if we assembled our linear combination of vectors like this, x1 times 1, 0, 1, x2 times 1, 1, 4, x3 plus x3 times 2, 1, 5, right? That would mean this is the x1 column, this is the x2 column, this is the x3 column. x3 is free, so we can generate a linear dependence relationship just by choosing anything except 0 for x3. So in particular, we could choose 1 for x3. So x3, we're going to choose 1. x2 then has to be minus 1. And x1 also has to be minus 1. So that means minus 1 times 1, 0, 1 plus, or minus, 1 times 1, 1, 4 plus 1 times 2, 1, 5 is the 0 vector, or should be if we solve this system correctly. And if you check my arithmetic, it does work. So now we can just solve for any one of these vectors. So of course, since each of these, what we've seen in the past is when you have a linear dependence relationship like this, you can treat any vector that has a non-zero coefficient in front of it as the redundant vector. So we could treat this vector as the redundant vector since it has a non-zero coefficient in front. To be explicit, the reason why this is the case is because as long as there's a non-zero coefficient in front, you can solve for that vector. So 2, 1, 5, we can solve this equation for it. It's 1, 0, 1 plus 1, 1, 4. So since this one is redundant, since 2, 1, 5 is in the span of the other two, we don't need 2, 1, 5 to get the whole span. The other two vectors span 2, 1, 5 itself, so you don't really need it. So that means W is the span of just these first two vectors. Well, are these first two vectors linearly independent? Well, in this case, yes, because we're down to just two vectors, and two vectors are linearly independent whenever they aren't multiples of each other, and that's the case here. So here we have a basis for, we have a spanning set for W that is also linearly independent, and so the number of vectors in this spanning set is the dimension of W, and so that's 2 again. All right, one final example. Let's find the dimension of this subspace, Z, which is all of the vectors, these are all in R4, of course, all of the vectors in R4 whose entries satisfy this equation. All right, well, what could we do? I mean, just the way that this is expressed, right, we don't have it as nicely set up as a span as the previous two examples. So we're going to have to somehow take advantage of this equation. And what we can do is, this equation is really saying that A is B minus C minus D. So we could put that into this vector. We get B minus C minus D, B, C, and D. And every vector that satisfies this equation will be of this form. And B, C, and D are arbitrary here, right? By sort of replacing A, we've already enforced this equation, so all the other variables are now free, essentially. So this is B, C, and D are just anything in R3. Okay, I'm sorry, anything in just R. All right, but now that we have our subspace written like this, now we can go back to our old trick of decomposing this single vector as a linear combination of other vectors. So this is going to be, let's see, B times 1, 1, 0, 0 plus C times minus 1, 0, 1, 0 plus D times minus 1, 0, 0, 1. And this is B, C, and D are real numbers. Okay, well now we've expressed this subspace Z as the span of these vectors, 1, 1, 0, 0, minus 1, 0, 1, 0, and minus 1, 0, 0, 1. The only question is, are these linearly independent? So we could do our usual thing by stuffing them into a matrix and then row reducing. But in this case, there's sort of a shortcut. If you take just linear combinations of the first vector, those will never have a non-zero third entry. So clearly, this second vector is not in the span of the first vector. And that means if you add this second vector to the first vector, what you get is a linearly independent set. Remember, if you start with the linearly independent set and you add a vector not in the span of the linearly independent set, you get a larger linearly independent set. So since just the first vector is linearly independent, the second vector isn't in the span of this, that means when we add the second vector, this resulting collection is still linearly independent. But we can do that again because this third vector is clearly not in the span of the first two vectors, because the first two vectors have a 0 in the last entry, but this vector doesn't. So this third vector is not in the span of the first two vectors. So the first two vectors are linearly independent. The third vector isn't in the span of them. And so if you add the third vector to this collection, the result is still linearly independent. Okay, so now we have a linearly independent set that spans Z, and so the dimension of Z is just the number of vectors in this basis, and that's 3. Okay, let's see what else we can do with this idea of dimension. So suppose we have k linearly independent vectors sitting inside of a k-dimensional subspace of Rn. What can we say? Well, let's give everything a name. So let's call these k linearly independent vectors, how about u1 up through uk? And this k-dimensional subspace, let's choose a basis for it. Let's call this the basis v's. So say v1 up through, well, how many vectors will there be in this basis? Well, it's a k-dimensional subspace, and that means that there has to be k vectors in this basis. Okay, so all of the u's are in this subspace for which we have a basis. That means that all of these u vectors, they're each in the span of the v's, like this. And also remember that each of these collections are linearly independent. The u's are linearly independent by assumption, and the v's are linearly independent because they're a basis. A basis has to be linearly independent. Okay, so since all of the u's are in the span of the v's, that means for each u, we can write it as a linear combination of the v's. So that means it's a sum from j equals 1 to k of v sub j times some coefficient, but the coefficient will depend not only on what j is, but also on what I is. And if we pile all of these equations into a matrix, what we get is the matrix u1 up to uk is equal to, let's see, the first one is, so we can form a matrix out of these v's just by putting them all in as columns, like this. And we can call this matrix V. And this linear combination of the v's, it's actually just v times this, the first column of the a's. So this is going to be a1i down to a ki, which we could probably just call this a, or sorry, I guess since I'm on the first column, I should have a 1 here. So a11 down to a k1. But we should just call this column vector a1. And so on down to the last column of this matrix is u sub k, but that's v times a sub 1k down to a sub kk, then we can call this a sub k. So really what we have here, this vector on the right, is just the matrix product of V and A, where A is the matrix whose columns are A1 through AK. Okay, so and this matrix here, of course, we'll just call this U. So U is V times A. U, since all the U vectors are in Rn, U has to have n entries, so n rows. And we know there are k columns here because that's how many U vectors we started with, so it's n by k. V is also n by k for exactly the same reasons. And for this equation to make sense, for the vector product to be defined, and for it to produce an n by k result, A has to be k by k. All right. Now, remember that the U's were linearly independent, right? And in fact, so were the V's. So let's suppose that this equation, A times x equals 0, has a non-trivial solution. Okay, well, if that could happen, then we could take this equation, take such a non-trivial solution, multiply on the left on both sides by V, and you get VAX equals 0. But V times A, that's U, so UX equals 0. And you'd have a non-trivial, and right, we assumed that our solution X was not the 0 vector. So here we would have a non-trivial solution to UX equals 0. But that can't happen because the U's are linearly independent. So this is actually a contradiction. So this can't happen because the columns of U are linearly independent. So we made an assumption. We said, suppose we have a non-trivial solution here. We derived a contradiction, and that means that this assumption must be false. So that means that what this tells us is that A times x equals 0 has no non-trivial solutions. All right. But remember, that tells us that the columns of A are linearly independent. But remember that for a square matrix, and A is square, it's k by k, remember? For a square matrix, if you have linearly independent columns, then it's invertible. So A is actually invertible. All right, so remember, we had this equation, U equals V times A, but now we know A is invertible, so we can multiply on both sides by A inverse, and that gives us U times A inverse equals V, right? But, this equation that we started with, this was because all the U's are in the span of the V's, right? But by exactly the same token, this equation on the right tells us that all the V's are in the span of the U's. So we already knew that the span of, so we know that since all of the U's, U1 through UK, are in the span of the V's, V1 through VK, this was an assumption we made at the very beginning. This tells us that the span of the U's is contained in the span of the V's. Right? If all the U's are in this span, then the span of the U's has to also be in this span. But now we know it the other way. right? We just showed that all of the v's in this situation have to be in the span of the u's, and that means that the span of the v's, span of v1 up through vk, is contained in the span of the u's. Okay, but look, this tells us that the vector space that we, the subspace of vectors that we started with is actually contained in the span of the u's, but the span of the u's is contained in the subspace we started with, but that means that really these are equal. These two spans are equal. So that means that U is a linearly independent set that spans span V1 through Vk. So all of the U's, U1 through Uk, are a basis for this span. And that's really the point of this whole argument. So let's go back to the top and summarize. Right. So we supposed that we had k linearly independent vectors in a k-dimensional subspace. What we figured out is those k vectors are a basis for that subspace. So really what this is saying is there's only one k-dimensional subspace sitting inside of a k-dimensional subspace, which kind of makes sense, but isn't totally obvious, so it needs proving. And now we have proved it, right? The biggest thing you can fit in a k-dimensional subspace is a k-dimensional subspace, and there's only one of them. If you have k linearly independent vectors in a k-dimensional subspace, that is actually a basis for that subspace. This can be a pretty handy fact just sort of on its own, but it has an important consequence. So let's suppose that we start with some linearly independent vectors, v1 through vk, contained in some subspace of Rn. Now, I'm not intending to imply that this is a basis. So these vectors v1 through vk might not span v, but they're contained in this subspace v. What I want to ask is it possible to start with this basis, or with this linearly independent set, and add some vectors from v to produce a basis for v? So if you start with a linearly independent set, can you extend it to get a basis for v? Well, let's see what we can do. If v1 through vk spans v, well, then we're done, because we assumed that v1 through vk is linearly independent, so if it also spans, then it's a basis. So then this is a basis for v. All right, so, but what if it doesn't? So what if these vectors don't span v? If not, we can choose some non-zero vector, we'll call it v sub k plus 1, that's in v, and here's the important part, this new vector that we're choosing is not in the span of the previous vectors. If the previous vectors don't span all of v, there must be something else in v that we can choose here. All right, but one thing we've seen in the past is if you start with a linearly independent set and you include a vector not in the span of that linearly independent set, the resulting set is still linearly independent. So v1 through v sub k, and then adding on v sub k plus 1, is still linearly independent. Okay, so now we can ask again. If this set spans v, then we're done, because we have a basis. If not, then just repeat what we did before. If these k plus 1 vectors don't span V, then there's something else in V that isn't in the span of V1 through Vk plus 1. So then we can tack on that new vector. So then we're going all the way up to V sub k plus 2. And then just keep doing this, right? If it spans, we're done. If it doesn't span, then that must mean there's some other vector that we can add into this. It's still linearly independent. And so now we have a bigger collection of vectors. So the only question is, does this process ever terminate? But remember what we just proved. As soon as this process has to terminate, because eventually the size of this set, so the size of this big set of vectors, will reach the dimension of V. But what we just proved is, if we have a linearly independent set whose size is the same as the dimension of the vector space, then it's a basis. So all we need to do is repeat this process until we have the same number of vectors in this collection as the dimension of V. Then this collection of vectors, which by this time will go from V sub 1 all the way up to V sub the dimension of V, then this is guaranteed to span V. Well, we still know it's linearly independent, but now it also spans V, and that means that this collection of vectors is a basis for V. Okay, so we did it. We started with k linearly independent vectors, and we were able to extend that to a basis for this vector space V.